an action potential. This is what our goal was, remember? To reach threshold so we have an action potential. Once you have an action potential, there are a couple other properties we need to discuss. To do that, let's bring in resting membrane potential, which in our example here will be minus 70 millivolts. How this graph is set up is that you're going to have time on the x-axis and you're going to have voltage or conductance on the y. And we have two different variables because action potentials and membrane potentials are in voltages and the various ions that travel through are measured in conductance. So let's look at what happens first. This is our traditional action potential where you have an increase that occurs initially and then you have a decrease that happens to bring it down towards resting membrane potential, a little bit below, and then finally it comes back up to normal resting potential. Sodium conductance is the main contributor to that initial spot of increasing membrane potential or depolarizing. So it's opening up sodium channels that cause this effect. What brings down the action potential is the potassium conductance. Why are they traveling in the directions they are? Because the membrane potential will want to go towards the equilibrium potential of whichever ion we're looking at. So if we open up sodium channels, it wants to travel towards the sodium equilibrium potential. If we open up potassium channels, it wants to travel towards the potassium equilibrium potential. Besides equilibrium potentials, there's one other thing we need to discuss, and that is refractory periods. Now, refractory periods can either be absolute or relative. And what is a refractory period? It is a time at which you can't start another action potential yet. If you're in absolute refractory period, there's no way to get another action potential. No matter how hard you tried, no matter how many EPSPs you gave, you will not get another action potential. During the relative refractory period, it is reduced, meaning you are at a hyperpolarized state, so it's going to take more effort to be able to reach threshold. So you would need a greater number of EPSPs than normal to try to reach threshold. And that is the difference between an absolute and a relative refractory period. Now, how do you get an action potential that started off at the soma or at the axon hillock all the way down to the next axon terminal? This is a propagation component. So once you reach the axon hillock here, you are going to have to jump it down the axon till you reach the next axon terminal. And it's these action potentials that are going to be moving down that axon. How does that process work? So how you get those axons to propagate? You need to utilize saltatory conduction. Now, saltatory conduction allows for a speedy travel down the axon. So what is the slow way down the axon? That is, you would do an action potential, action potential, action potential, action potential, action potential, action potential, all the way down to the end. I mean, I can hardly say that many action potentials. The other way to do it is have the action potentials jump. And that is what saltatory conduction is. The jumping of an action potential from one node of Ranvier to another. These nodes are the spots that you can see here that have a high sodium channel density. So when the sodium channels open in one node of Ranvier, they can then transmit it all the way to the next. This is an important process of not needing to do as many action potentials down the axon. So this is a fast propagation. You notice that there are a lot of space in between each of these sodium channels. That space in this particular diagram looks blue. In fact, it is another cell that's wrapping around that axon. So let's talk through what that might be. Myelin is going to be an insulator that is allowed to wrap around an axon. Its form and function is going to be primarily as an insulator, and so you have a less current that is lost across the axon. If we look at any individual form, you will see that there is a cell, you'll see the axon, you'll see it grows by wrapping itself around till it's very tightly wound. A little bit like electrical tape. If you were to tape up a wire, you are simply wrapping a number of different iterations around the wire. Its function, again, is to allow for jumping of action potentials from one node of Ranvier to another.